I'm Joey Syracusa. I'm electrical computer engineering. I handle most of the computing related things.
I'm Andrew B. I work with Joey on most of the computer related things, mostly software side.
Alright, so AggreGator is an autonomous mining robot made for extraterrestrial mining. Originally, the competition is meant for mining lunar soil called BP1 regolith, but this year they're actually changing. They kind of change the rules a little bit every year, and this year they're modeling the soil that we're mining more towards the Martian soil. And we build a robot from scratch. We buy all the materials, we program it, we model it in SolidWorks, we program it in ROS and model it in SolidWorks, and we go to the annual mining competition every May.
I just have a quick question. Where did the AggreGator name come from?
It aggregates soil.
Gotcha.
That's the
Hey.
Hey. Gotcha.
Alright, so we design and test software, electrical, and mechanical systems from scratch. We design it, we try and figure out what the most optimal design is, and then we have to build it from scratch and test to see what works, what doesn't work. So we're going to end up applying practical skills, and we work with SolidWorks, ROS as our programming system, Odroid, and I2C. And the competition is actually held in a Caterpillar arena at NASA every May, in like in this little simulated environment with just like pits with the soil that we're mining in it. And we do outreach at local events such as this. And we're actually gonna skip that.
Let's get a picture though. So
yeah, that's a good
that's
picture.
That's a picture of the arena. You know, our robot's on the right. There's another team's robot on the left, and so right now this is just the start. So both teams have 0. There's 3 sections of it. They start at the very, very back. The middle section is like an obstacle section. It has craters and rocks that the robot has to get over. And then the section closest to you is the mining section, and that's where the robot actually picks up dirt. And then has to bring it back to the very back of the section where they are now, and dump it in the specialized bin that calculates the weight of the BP1.
Okay.
Yeah, and it's a minimum of 10 kilograms to
qualify.
qualify.
Yeah, so last year, this was kind of like what our previous design was. So to the left is the CAD model of our design, and then to the right is with it fully assembled with the mining assembly on there. We don't actually have the mining assembly right now with us just because it has a lot of weight to it.
Yeah, I think it's huge.
Yeah.
The motor on the side is extremely heavy as well.
Yeah.
It goes very fast, very powerful motor. But we're rethinking it this year a little bit. But sorry, go on.
Yeah. So essentially, what we went with was trying to do kind of like a rocker bogey type design. If you're not familiar with that, it's what NASA uses on like their Martian rovers. They have about like 6 wheels and 10 different motors to like control that entire thing, so that when they like go over rocks, they're just like solid and steady, so that none of their equipment gets broken. We're more of an industrial type robot, so what we did was a modified rocker bogey design that didn't require like 10 motors just to control it. We just essentially have these 2 wheels right here that are just kind of connected at like about probably a 45-degree angle. And then they run on this shaft right here that has a differential in the back right here that connects over to this other side. So then when we go over like a rock or an obstacle, like
All
that,
4 wheels still stay on the ground.
yeah, this wheel gets pressure puts down on that wheel, and then like this differential keeps pressure put on both of these wheels, so you don't have a situation where you're going up a rock and then one of your wheels comes out of contact and you start skidding out and get stuck.
Tilting.
Yeah.
Yeah, we were actually about the only team, if not the only team, that actually had a suspension system at the competition, which is really interesting because this is essentially sand or dust. Like it's just a giant pit of dust, so you can lose traction very easily and get yourself stuck very quickly.
Yeah.
And then we also, for our mining, we went with the concept of what they call a bucket drum. It's a pretty experimental concept right now. Like the only paper we could really find on it was like Lockheed Martin like made one, and we just kind of tried to copy their design a little bit, or just kind of use it as a reference.
Yeah.
And essentially, it's just supposed to be kind of like you have a circular drum with these scoops on the outside of it, and you push it down into the ground, and it just kind of takes the dirt out like just one scoop at a time, but you have multiple scoops, so you're getting a lot of dirt at once. And then to prevent the dirt from just falling back out, like as the scoop comes down the bottom, there were like these kind of like what they call baffles on the inside. They're just kind of like paddles on the inside of it, so that when it's in its downstroke, it's not going to lose a lot of dirt.
Right.
And the design worked. It held dirt. Unfortunately, at the competition, we either did not have it in a position where it could like freely mine. Like when it would go down, it would start doing these cans just because of like kind of some manufacturing issues. Or what would happen is that we were able to get it down and mine, but then we couldn't, like because of our modification, we weren't able to raise the bucket drum high enough over the bin to actually dump it.
Oh, okay.
So those are the problems we ran into with it. It also only held probably about 2.5 kilograms at its maximum. So we'd have to make about 5 trips there and back in that 10 minutes, which would be very difficult for us to do. So we didn't end up qualifying at the competition, but we did learn a lot from this project, or from this year. And so now we're coming in full swing this year, and we should qualify, if not do much better.
Yeah. Who won? Like do you know who won the competition? Like what school?
What was that who won? I think it was West Virginia University who won.
It's actually a funny story that the team won. They announced who won like at the competition, and then weeks later they figured out that they counted the points wrong, and they had to take away the first place prize from that team and give it to different teams.
Oh man, that's
I
terrible.
can't even remember who the other team was, but one of them was Alabama, I think, and then I don't remember the other one.
Oh wow.
I believe it was either Alabama and West Virginia. I know Alabama was there at the very, very top. It was like the top 3. And then
Wasn't there Florida Atlantic in one of those?
FAU was there.
Or yeah, FA, I think. Or not FAU. There was a Florida school that placed like top 3 or top
I think it was
5.
FIU.
It might have been FIU.
FIT? Like,
But
I think I mean FIT.
Yeah.
yeah, or FIT.
FIT.
because-
I know FIT
Yeah, my
was
friends
doing
are
really,
there.
really well in the mining competition
Yeah.
that year.
Yeah.
Yeah, so this is our current design. So it looks a lot different from the design we have right now, but we did take a lot of the elements and issues that we had with this design and applied it to like this one. So what we went with tracks instead of the suspension system, because the suspension system had really good weight distribution and tracks also have really good weight distribution, so we just decided to go with tracks because also what happens with this design is it keeps us off the ground and it works really well, but it also kind of, like you can see, there's kind of some spatial issues like with the mining assembly, so it makes it a little bit less modular and as far as the mining assembly is concerned. And we changed our tactic to mining as much regolith in one run as possible. So
you can see like there's a lot of empty space on the spot, and there's size requirements. We can't just build a massive bot. So we love the suspension, but it's just too big. We need a bigger bucket.
yeah, we just need a bigger bucket, and if we were to try and make something like that kind of top heavy with a system like this, it could make it like too top heavy and it could like fall over or something like that. So we went with what they call a bucket ladder, which is like kind of, as you can see, there's just scoops that are attached on like a chain drive, and they just kind of like scoop the dirt one at a time, and they just keep dumping it into that main hopper. And then the interesting thing is that we made the main hopper dump separately from the bucket, so that we don't have to have like a really, really huge like linear actuator to try and dump all of that.
So how do you test it for a competition? I mean, do they tell you like what the bot is supposed to do, and do you have like some sort of makeshift like Mars,
They pretty much send out like this like 20-page set of rules for us that we have. Essentially, we have full authority over the design and materials we use for the robot, except for like explicit things they won't let us use. They're much more specific in how they allow us to use our software, as well as like the hardware we're allowed to use.
Networking as well, because they implement a lag, because they want to try to simulate the delay it would take to communicate with a bot far away. So they're really strict about networking rules and how you can communicate with a robot. But you have a lot more free reign with the mechanical stuff.
Yeah, they don't really have a lot of requirements on the mechanical items, really.
Pressurized air, unless you bring your own pressurized air.
Yeah, there's stuff like that. Man, let me think.
The size requirements are the most difficult rule to satisfy.
Yeah, there's some size requirements.
Okay, and for test runs, do you like take it outside or something?
Test runs,
and
we
make it-
last year we didn't have too much time for testing, but the biggest thing we did do was mostly in the volleyball courts.
Okay.
And we tested, just how we pick up normal sand. We don't have access to BP1. That's one of the most difficult challenges about this. Is we're working with like this odd regolith. It's very, very fine. It can destroy electrical systems if we don't have it protected properly. So that's one of the biggest challenges. We don't have a BP1 testing bit. We are working with. We've discussed with our professor about maybe setting one up, and we're hoping we're going to have that next semester, but it's still all up in the air, so we'll see.
Okay.
Yeah. Yeah, there's just a couple more pictures of our, just kind of like close-ups of the different design elements I already mentioned.
Drive train, bucket ladder, and pneumatics and electronics.
Okay, so I'll go over the electronics a little bit. So our power system, we just run on LiPo batteries. They're all 24 volt LiPo batteries. We have 3 of them. We plug them all into the same one that we want, to last for a long time, but it can run fine on one battery. Power monitoring, we don't have any power monitoring right now, but last year we did have a current sensor on our microprocessor. It sends current on our microprocessor, so we can measure how much power the electronic system was using. To communicate with our bot, we have just a Wi-Fi dongle connected to our bot's main computer, and it connects to the router that we own, and it's our own team's router. And then we plug in directly into that router with an Ethernet cable, but at the competition, we would connect into NASA's network.
Okay.
And NASA would slow down the traffic, so there's massive delay, and which can be very challenging to control a robot, because you do something too much, you hit a wall 10 seconds later.
Right.
So for the control electronics, our main, and I can't take them out too much, but our main computer is this. It's this computer on like a board. It's an Odroid. Just think of a Raspberry Pi. It has everything that a normal computer would have, an operating system included, but it's a little bit more heavy duty. It's got massive heat sinks on it. It does a lot more. But it's got a bunch of USB ports as well. So that's our master. That's what we communicate with our computer at. And then it talks to teensy Arduinos, which are little Atmel processors. You guys, I guess you guys may be covering Arduino soon, but maybe not. But so we just use Arduino to control things like the pulse width modulations for the motors, so sending signals to the motors to tell them how fast to go. And we also have them do some current sensing for voltage sensing for our sensors. So we're going to have IR sensors to sense distance and obstacles. And we're going to have a couple of other sensors, like an IMU to sense if we're level or not, and acceleration. So those are the types of sensors we have. And then actuation. So we had linear actuators on the front to control the bucket drum being lifted. We don't have that on there right now. So we don't have the actuation done right now either. But that's going to be something in the future. To protect all the electronics, we have this massive waterproof box that everything sits in. It's BP1 safe. We've had no trouble with that at all. Like all our electronics are perfectly clean when we got it back from the competition, so that was really great. And I don't know why schematics is there. We don't have any schematics with us right now. But
It's just from last year, just
Okay.
like overall electronics topics.
So that's what we're doing right now. The Odroid our main computer, acts as a master, and it writes I2C messages to all the other devices that we use. I2C is just a standardized way of communicating on a massive bus. So, it's very modular. We're able to add new sensors, take away things whenever we want. We're thinking about breaking it up even more so that we have multiple microprocessors controlling individual pieces, like very, very tiny ones instead of an Arduino. So that's still in development, and we'll also be printing a board next semester, so that's pretty exciting too. But that's most of the electronics.
Right.
Wow.
And so,
Oh, we didn't talk about ROS, I'm sorry.
oh,
You want to talk about ROS?
Sure. Well, ROS runs on Ubuntu.
It's a robot operating system, I'm sorry.
Yeah, that's what it stands for. Basically, the idea of it is that it handles things like message passing, parameter set, simulation, various things that you would use in not only testing robotics, but also running a system for any kind of robot. There's a lot of pending packages for it, like integrated drivers for certain sensors, packages for parsing and just generally processing any kind of data, visual data,
Like LiDAR data.
LiDAR data. Generally, you can use C++ or Python to program modules for it called packages. And it doesn't matter which one you use actually, because it relies on the message passing mostly. You can interact between Python programs and C++ programs. Besides that, I mean, you don't need to use it to actually get a functioning robot, but it does help a lot. It takes care of a lot of the dirty work.
It's very convenient. It allows you to break up your robot into separate nodes, so you would make individual packages which have a collection of nodes. So you'd have a package for each type of, sensor that you have, and you're allowed to break it up and you can easily see which messages are going where. It's very convenient for like the higher level software stuff.
Is it like open source, or you have to buy that, or
What's that?
is it open source?
It's
Do you
open
have to
source,
purchase it?
yeah. It's MIT made it. It's under the MIT license if you guys know what that is, so anyone can use it.
Mhm.
It's really great. It's really helped us a lot.
Okay. Well,
Yep, so we don't have too many people right now, I don't think, on with electronics or software. So if you enjoy programming, or if you have any experience with ROS, or if you want to learn how, and you're interested in the lunar mining competition, then consider joining our team. So, and any help's appreciated. We have meetings on Mondays, Thursdays, and Fridays from 5 to 7. It's in MAEB, right?
MEA, or no, MEC 010.
Yeah,
Okay.
it's like, if you go around the back, it's like the middle door. Yeah, we just work in the lab there. It's right next to the garage where you might see people building a car,
yeah, yeah.
like all the time, like every day.
Yeah, this is on there. It's a shared workspace. We share it with a couple other teams.
Yeah.
Okay. You guys work with, what professors do you work with?
Right now, our faculty advisor is Dr. Griffiths. Mike Braddock's the one who runs the lab for SAE, as well as pretty much he's in control. Our lab is under his jurisdiction, actually.
Okay, okay. And what's the first place prize if you guys win this competition? Like the lunar competition?
There's a couple different prizes. If we win the mining portion of the competition, we get like a $3,000 scholarship, and then we get to go see a launch at Kennedy Space Center.
Oh, okay. That's cool.
And then there's a couple other prizes similar to that, just in their other categories.
Yeah.
For whoever gets the most points in like every single category, you get the Joe Cosmo Award,
Yeah.
and essentially you get a $5,000 scholarship and then invitations to launches. And there might be some other stuff, but that was pretty much the big name prizes.
You get a job at NASA?
Or a job at Caterpillar, probably. It's a sponsor.
I'm sure you would if you asked nicely.
Okay, cool.
But yeah, it's a really difficult challenge, but we're working hard at it. So we could use help. We definitely need help with software stuff. Most of us are ECE or electrical based or mechanical based.
Yeah.
These are only like pure software guys.
Right, right.
But yeah, that's about it. Once our two buddies get back with the remote control, we'll actually get to drive it around. But we don't have a remote controller just yet.
Okay.
Yeah, I mean, we especially need software too because we're trying to make this autonomous for this gears competition. So that requires a lot of software knowledge as well.
Yeah, right now we're still controlling it, which still took a lot of programming to do, but it has a long way to go. So, working on it. But because that lag especially, it's so hard to control with that lag. It's really great if it would just drive itself, react immediately to this environment. So that's the goal.
That's pretty much it. We have a website with some photos and stuff on it right now. UFAggregator.com. That's pretty much it.